Hello and welcome to today's webinar presented by Dlubal Software. Today we will be working in our finite element analysis and design software, RFEM. The topic for today's webinar is ACI 318-2014 Concrete Slab Design in RFEM. My name is Amy Heilig. I'll be your presenter today. I'm the CEO of the U.S. office. I'm also a technical support and sales engineer. Our office is located in Philadelphia, Pennsylvania. My colleague Moritz Bertram will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way of the presentation when you logged into this GoToMeeting, you can show or hide that with the orange arrow up at the top. We want to encourage everyone to ask questions throughout the webinar. You can use the same dialog box to do so. We'll do our best to get to all of them, but if by chance we don't, I will certainly send you a follow-up email afterwards. As far as the content today, I first want to describe our software and how our main program RFEM and the add-on modules work for concrete structures, for those of you who may not be familiar with our software. And then after that, we'll just jump into a two-way concrete slab design. Here we will do an analysis in RFEM to kind of show you what's entailed with RFEM alone. And then we'll do ACI 318-2014 reinforcement design using our add-on module RF-CONCRETE surfaces. We'll also be taking a look at deflection in regards to creep and shrinkage using our add-on module RF-CONCRETE Deflect. And throughout the example, we'll be taking a look at our results, evaluating what they mean and how they can be applicable to our design. And then lastly, I want to show the export of the reinforcement data to maybe a few other programs that you're familiar with, but that we do integrate, so that maybe you can do some reinforcement design details, some drawings in programs such as AutoCAD and other reinforcement programs. So the concept of the add-on modules for concrete design. Our main program RFEM is where you're going to be doing all of your loading, your modeling. You can apply your load combinations according to different standards. We integrate with BIM software such as Revit, Tekla. And you can also run a full analysis in RFEM. So if by chance you're just simply wanting the internal forces such as your moments to do your reinforcement design by hand, then by all means you can do this in RFEM alone. Now our add-on modules come into play when you're wanting to do reinforcement design according to the ACI 318-2014 and several other international codes. For our concrete structures, RF concrete, we kind of have two segments here. On the right-hand side, you can see that we have RF concrete members and columns. And if you were present at my webinar that I gave about a month ago, I really just focused on the design of beams and columns for strength and serviceability limit state design. We also took a look at deflection analysis according to the ACI 318-2014. So this is really only for framework type structures. Now our other program, RF Concrete Surfaces, that you see over here on the left, this is for any type of slab element, surface element, walls, plates, shells. And here we can also do a strength and serviceability limit state design according to the ACI 318. We also have several international codes for all of these modules as well. Now, as far as deflection, today we will be using RF Concrete Deflect. So RF Concrete Deflect is a linear elastic analysis to take into account creep and shrinkage. Now, it is integrated directly within our RF Concrete Surfaces add-on module. We do have another add-on module called RF Concrete Nonlinear. This is for nonlinear analysis. It's a more exact approach, and this will use our exact crack sectional properties to calculate our deflection. RF Concrete Nonlinear is only available for serviceability limit state designs in these add-on modules. We will not be getting into this today, but if you by chance want to get into more of an exact approach, then this is certainly the way that you want to go. And with that, we can jump directly into our RFEM model. So in order to save some time here, I went ahead and modeled a basic slab here. Now there's quite a lot of other details going on, but you can see that as I hover over these 4 slabs, I created them as 4 separate slabs because these 2 smaller slabs over here are being cantilevered out from our supports. This will come into play later on when we're doing a deflection analysis. Now, we also have some supports applied here. So maybe this is an elevated slab type application where we have some walls framing in underneath as well as some columns. And we need to either model those columns and walls or take into account with surface supports, or sorry, with surface line supports and nodal supports. So you'll notice here that this is a particular line support. And if I double click on it, a line support, we have our typical hinged and rigid, and if I go into my application, you'll notice that we also have the ability to define spring constants for partial fixity. We have nonlinearities, things like sliding, friction. We can have a failure in case of a specific moment or force. But we also have this very useful feature called an elastic support. And that's what I'm utilizing in this example here. If I go to my wall parameters for line support, the only thing that I need to define is essentially the width of my wall, 8 inches, and I define the height as 10 feet. Then I give the wall a specific material, 4,000 psi concrete, and I define the support conditions at both the top and the bottom. Now you'll notice that the program automatically comes up with these effective spring stiffnesses to apply in the model, and they're applied to every single FE element along the length of that line support. So rather than manually entering in what should be these effective spring stiffnesses, you can take this all into account by filling out this edit wall parameters here. So it's a very useful feature. And in the same sense, if I zoom in here, we'll assume that this is maybe some type of column supporting it from the underside here. If I double click on my nodal support and go into the details of this, I have that exact same option but to take into account a column instead of a wall. And I go into the details here. Again, I'm just kind of defining some of the geometric properties such as an 18-inch by 18-inch column. I give it a material, concrete, 4,000 psi, define the height as well as my support conditions at the top and the bottom. And then again, the program is coming up with these effective spring stiffnesses in both the translation and rotation global directions and applying it into the model. So this is nice as well for issues like singularities. With finite elements, sometimes we get singularity where we're applying all of this load at this single node here. Well, these specific type of supports help distribute that load over the column head, 18 inches by 18 inches. So essentially, those are just some automatic features we have in the program to take those other elements into account. You'll also notice that I have my finite element mesh defined here. The default is 1 foot by 1 foot. Maybe around these particular column locations, though, we'd like to define more of a smaller finite element mesh. Now, we could do so for the entire model, but the problem with that is that it's going to really significantly slow down our solve time. So that's why in RFEM, we give you the option for FE mesh refinements. And what we have is FE mesh refinements about a particular node, maybe a line, a single surface, or a single solid. And you can see for this application, I defined this FE mesh refinement about this node. I gave it a radius of 3 feet. I gave it a target FE length on the inner and outer sides. And then what the program is going to do is it's going to transition quite nicely from the smaller FE mesh into the larger FE mesh back into our global settings. So again, this provides a smaller FE mesh without slowing down our solve time because we didn't change the entire structure here. Now, in regards to the ACI, it does tell us that we need to take into account some stiffness modifications for slabs. And again, if you were present at my webinar last month, we did the same thing for our columns and our beams. I'm just going to drag my selection box over all of my surfaces. I'm going to right-click and select surfaces to edit all of them at once. Now, if I go to this tab called Modify Stiffness, the default in RFEM is to have this set at none. And what you need to keep in mind is that if you're doing any type of ACI design for columns, members, walls, flat slabs, you need to modify this stiffness here according to ACI. So we have this simple drop-down box, and now the only thing that I need to do is to select my component type. So last month we selected columns for our column elements. We did a separate selection for our beams, and for this example we want to choose flat plates and flat slabs. Now this is going to multiply my bending stiffness by 0.25. This just comes directly from the code to take into account cracked sectional properties to reduce our stiffness. So we will leave all of these flat plates and flat slabs with this multiplication factor. Now, the other thing that we get asked quite often is how to take into account a one-way versus a two-way slab. So when I go to draw in my typical slab surface element under my General tab, you can see here that my stiffness is set to standard. I've defined my thickness as 12 inches. So a standard stiffness means a two-way slab. We have really no boundaries in regards to our load distribution with any which direction on this particular surface. So I'd consider that a two-way slab. Now, a one-way slab, which is quite common as well, can easily be taken into account as well. So instead of the standard stiffness, we'll want to choose orthotropic here. And you'll notice that a few of these examples pop up when I choose orthotropic. I can use this edit parameters box, and up will pop a new dialog box to kind of take into account these different stiffness modifications. Now, the first one under this General tab is constant thickness. This is my standard surface type. Really, there's not much going on here other than in the same sense as the standard surface, but now I can see my stiffness matrix. It's nice because it is divided up into sections. It's very easy to read. We have bending and torsion. We have shear, membrane, eccentric effects. But back on this General tab, if we click the second option, effective thickness, now I can click on my second tab here, effective thickness, and I can define this effective thickness to control my stiffness properties in both the local X and the Y direction. So let's say, for example, in my local X direction, I would like this to still be 12 inches thick in my X direction, but my Y direction, I really want to decrease that stiffness because I have this one-way slab really spanning with my load distribution in the local X direction. So my Y direction, I can maybe give this a thickness of 5 inches. So now my transform stiffness matrix will really take that into account. You can see here some smaller values for D22 in comparison to D11. Going back to my effective thickness, what's also great about this is we think, okay, well, we've changed our thickness, but what about other options such as our self-weight? Well, we've implemented an option down here under thickness to still take into account the full 12 inches for consideration of self-weight. So really the only thing that we're affecting here is our stiffness. So that is an option for a one-way slab. Now back on the General tab, we have a few other options. For example, defined by stiffness matrix. You can enter in your own values here for your stiffness matrix if you do know them. We have a unidirectional ribbed plate, a bidirectional ribbed plate. You can see it's denoted here by these pictures. If I click on the second tab here, what's great is that I only have to define the geometric properties. So what you're seeing in this picture here, I simply define these length directions in these value boxes, and then the program will automatically calculate the transform stiffness matrix for me. Something like a trapezoidal sheet might be useful for a metal deck. We also have hollow core slabs and unidirectional box floor, so maybe something more like a box girder type application. Again, the only thing that you have to define are these geometric properties, and the program will automatically take that into account for our stiffness. We also lastly have grillage, which is maybe something more like a waffle slab. Again, just defining those geometric properties on this second tab here. So for our particular example today, we will be doing a two-way slab, so we will just stick with the standard slab stiffness. One last thing to take a look at are our loads. So if I turn this into the ISO view here, and I turn on my loads, I can see that I have applied a dead load, just a typical kips per square foot area load on all of my surfaces. Now I also have 4 different live loads applied. If I scroll through these 4 different live loads, you can see they jump around on the slab. Maybe this is representative of something like office loading, where you might have some part of the structure loaded but not other parts. Maybe all of them will be loaded at one time. And again, this is quite a common question that we get, is how do we load our slab so we're not loading the entire slab, but maybe just a portion of it? And that can easily be done with our free loads. Using our drop-down box here, we have free concentrated loads, free line loads, rectangular loads, circular, polygon, and variable. If I double-click on one of these free loads to open up the dialog box, you can see that we have everything here. It's pretty self-explanatory. You just go through it one by one. The first thing we need to choose is a projection plane. So we want to project this load in the XY plane. We want to choose a load direction, and you'll notice that my little picture up here updates as I choose these different options. So it's nice I know exactly how I'm applying this load. I want to give it a magnitude, and then I just simply click 2 locations, 2 clicks on this slab to define my rectangular surface area. This picture looks a little bit odd, and the reason for that is that we have a very useful feature. If you are doing an elevated slab design, but you have multi-levels of the same elevated slab, 10 stories high, and you know that you're going to have the same type of office live loads on each level, well, we have the option to actually project down through a series of slabs depending on what plane you choose here. So by choosing this option right now, it's set to all because it really doesn't matter. I only have one plane in my XY direction. But if you had multiple surfaces on top of one another and you choose those surfaces that you want this load projected down onto, you can do that with the click of a button. So that's nice that you're not individually having to apply each of these free loads at each level. And lastly, if we go to start a new model, or once I've created it, I can right-click on my model name and go into my general data. The program asks us if we want to consider load cases and combinations according to a specific standard. We can automatically create these load combinations. We have the ASCE codes, the IBC codes, we have Canadian codes, as well as many other international codes. I have this checkbox checked on to create these load combinations automatically according to ASCE 7. You can always turn this off and create your own manual load combinations, or you can do both. So for our load case, since we are doing ASCE 7 load combinations, you can see under my combination expressions that my LRFD load combinations will be created according to this orange box, and then I have my ASD load combinations according to this red box. If I click this info button, it will really show me which load combinations are taken into consideration directly from this code. Jumping to the load combinations, really drawn out here considering all of our applied loads. I wanted my live loads to be applied in all different scenarios. Maybe we have live load 1 and 2 acting at the same time, 1, 2, and 4, but not 3. Well, the program can automatically take that into account because under our Actions tab here and my live load, I've set this as simultaneous. So basically, the program's going to come up with all of the different scenarios that these live loads can act together. We also have the options for alternatively or differently here. So then I have all of my LRFD load combinations listed here in the orange and all of my ASD in the red. Under my results combination, this is nothing more than an envelope solution for our LRFD equations and the envelope solution for our ASD load combinations. So everything that you've seen up till now involves RFEM. And like I said, we can easily run an analysis now to get our internal forces to do our design by hand. But what the purpose of today's webinar is to show you guys how to utilize these add-on modules in order to do design according to the ACI code. So the first thing that I'm going to do is I'm going to launch my RF Concrete Surfaces add-on module. For those of you who are not familiar with our software, this is an add-on module, nothing more than a simple dialog box that pops up within RFEM. All of the information that we previously modeled in RFEM will be taken into this dialog box, such as loads. You can see here our load combinations are already brought up, materials, geometry. So you really don't have to worry about redefining any of that information. It's all correlated and synced together. Now, this particular first case that I'm going to run, I'm going to rename it. And you can see the default's just reinforced concrete design. I'm going to name this strength. For this first case, we're going to focus on just the strength limit design here. So what I first want to do is to select all of my LRFD load combinations for design. You'll notice that I use the drop-down box here to select ACI 318. And then the only thing I need to do is just to simply work down this list here. So I have my materials lists here, again brought in from RFEM, 4000 PSI, grade 60 reinforcing steel. I can quickly change this if I'd like to within the module. I don't have to go back into RFEM. All of my properties for my materials are listed here. I have a nice stress strain diagram for both my concrete and my steel. Moving on down to surfaces, nothing too extravagant here. This will change later on when we're considering serviceability, but for strength, it just simply lists our 4 slab types and then the depth of each one. Notice too that everything with these tables are synced up to the graphics behind it. As I scroll through these different slabs, you can see the red dotted line highlighting which slab I'm actually clicking on in the table. And lastly, we want to jump to a reinforcement. For our reinforcement, you can create as many groups as you'd like. So perhaps you have different slabs with different loads, different thicknesses. Of course, you're probably going to want to consider different reinforcements for these slabs. You don't want to have a one-size-fits-all for everything. So we allow you to create more than one reinforcement group. And you can see here that right now I've applied it to all of my surfaces by checking this checkbox. But by all means, you can apply to an individual surface, a group of surfaces, or all of the surfaces. For this particular case, we'll just choose one reinforcement group. You can see here my reinforcement ratios on this first tab. There are a couple of defaults already set. You can change these. The ACI code tells us that maximum reinforcement percentage, basically this is to avoid brittle flexural behavior in case of an overload type situation. In the newer ACI codes, essentially, they've gone away with the reinforcement percentage, but now are more focused on the net tensile strain of the concrete being greater than or equal to 0.004. So what the code's telling us is that you can essentially mess around with these percentages as much as you want, as long as those net tensile strain limits are met. 7331 and 8331 from the code refer to both one-way and two-way slabs, and they both state the same thing, that net tensile strain must be met. Reinforcement layout. This is just simply what is our cover. You can see here that I can measure my cover to the centroid of the reinforcement or to the edge. I personally like to measure to the edge. It's what the code refers to as well. The first thing that I need to do, though, is to tell the program what bars I plan to use. So I maybe want to start off with number 6s. So here I'll type in my diameter of 0.75 inches and measure my concrete from the edge rather than the centroid. Concrete cover comes from section 26.1. There are quite a few stipulations that you want to take into account. For our example here, I'll just set this as 2 inches to measure from the edge of the concrete to the edge of our bar diameter. Something interesting here, we have the angles set at 0 and 90 degrees. So this is we have 2 different reinforcement directions, and right now they're set 90 degrees apart from each other. But you have all the control in the world to change this if you'd like. You know, not everything is as simple as we want, especially with more complex designs these days. So maybe you have a load distribution type that maybe calls for something more like 45 degrees for your second reinforcement direction. That's totally possible here. It doesn't have to be your strict 0, 90 degrees. You even have the ability to add in a third reinforcement direction, say 0 degrees, 90 degrees, and 45 degrees. So really a lot of control here, kind of outside just your simple square slab design. We try as much as possible in RFEM and our add-on modules to give you a lot of that control. Longitudinal reinforcement. This is our provided basic reinforcement. At this moment now, I'm going to leave this all as zeros. I want the program to tell me what is my required reinforcement based on my applied loads. I don't want to have any influence at all right now by saying, okay, well maybe I'll try number 6s at 12 inches on center. I just want the program to tell me what's required. So that's why I'm going to leave this all as 0 for right now. Down at the bottom here, we have a few options. Basically, we can increase our required longitudinal reinforcement to avoid shear reinforcement. You know, some design situations call for the situation where you don't want any shear reinforcement, but rather we'd like to increase our longitudinal reinforcement, which in that case you can certainly select this option. For us, we will be designing both shear and longitudinal reinforcement. ACI 318.14, this is just some standard references. Minimum longitudinal reinforcement for plates is selected right now. We also have walls if we were doing wall design. Minimum shear reinforcement and nominal shear strength, some standards here. Our strength reduction factors come from the code, section 21.2.1. If we've done any type of concrete design, we're familiar with what these strength reduction factors are, and the default is set what the code calls us to do at the moment, but you can certainly change those as well. Design method. Here we can design for optimization of design internal forces or no optimization. I have this left as a default for optimization of design internal forces. And the only thing that we need to do now is just to run a quick calculation. So what is going on in the background is that we're running all of those LRFD load combinations in RFEM, and it's bringing all of these internal forces into the add-on module so that we can get our reinforcement strength design. Then all of these results will be shown directly in this add-on module. So you can see here that our results tab popped up down here at the bottom after we ran our analysis, and basically this total will just be a summary of what's required. I have my AS1 in the top direction for both 0 degrees and 90 degrees. I have AS1 and 2 in the bottom direction, so that's 0 degrees and 90 degrees, and then I have my required shear reinforcement. What's also nice is that we have this little design details button down here. If I click this, this is all of the information that you could possibly need to understand where the forces came from, where the design numbers came from. You can see here that these are all collapsible, so you can really get into detail. What I really pride our program on is we're not a black box program. We get very little tech support questions on people not understanding, engineers not understanding where the numbers came from within the program. So we try and give you as much information as possible. And what's great too is that we even show you the FE mesh point, and we show you where you're at on your slab surface. So this is our slab surface that came from RFEM. You can export all of this information to Excel at the click of a button to do some further sorting. You can print this information. We can easily jump to our longitudinal reinforcement down here for both top and bottom, and to our shear reinforcement. So again, if you have any questions about where this design information came from, that's probably available in this design details. We can also view this reinforcement design for each surface. Again, we correspond, or we synchronize the table with the view in the background in RFEM. So this big red arrow is always going to tell us where we're at according to this point number here, and the surface is highlighted as well, showing you which surface you're looking at, which we're looking at surface number 1. And then we can view it by point. This is a rather extensive table, as you can see. These are the different FE mesh points throughout the program. Again, as I click through them, the picture in the background will sync with where I'm at on the table. So this is all great in terms of tables, but probably we want to view something graphically to kind of get a sense on what is the overall behavior of our slab. So all I need to do is just to click my graphics. Now, looking at my slab, you notice that I have these nice contours now. I now have this Results tab available in my Project Navigator. I know I'm in my Concrete Surfaces add-on module still because, as you can see, I have all my different load combinations, but we have RF Concrete Surfaces selected in our drop-down box. Now, I can see my required reinforcement. I have my nice table here to show the different contours and in inches squared per foot, what exactly is going on. If I take a look at my reinforcement direction, I have this red arrow indicating which direction my reinforcement is spanning. Now I can scroll through my AS at the top in the 90-degree direction. And it makes sense what our contours are showing here. For our top reinforcement, we're going to need more around these column and wall supports because we have a negative bending moment. So we're going to need more reinforcement in our tops. Now, if we look at the bottom reinforcement, it's going to make sense that we're going to need more reinforcement at the areas spanning between our supports because this is an area of positive moment. We can also view AS bottom in the other direction, and you can see here that we have quite a bit more reinforcement needed for this direction. So contours are great, and I think it kind of gives you more of an overall sense of what's going on, but we also have an option for sections in the program. And what a section will do, and that's what these black lines indicate here, I went ahead and created some different sections throughout the slab. This is basically a cut right through the center of the slab. And the first thing that we can do, we can turn off our ISO bands for our results. And to create a new section, I can just simply go here to create section numerically. Now the program's asking me if I want to name it. It's asking what should we put the section through? We want to put it through a surface. I just simply need to click 2 points. I can always use my drawing grid to make sure I have a straight line here. And then just the projection direction here. And what's also great is that we can select all surfaces here, or we can maybe we only want to view this section for a particular slab. Well, everything is in your control within this dialog box. So I went ahead and already created these surfaces, as you can see in both directions, and then we can just simply turn on our surfaces at the click of our button instead of the ISO lines. Then we have the sections over here, and here is where I can really control what I'm looking at. You'll notice that right now I have my reinforcement direction for my AS2 bottom, so I can see my reinforcement is spanning in the north-south direction. But now I'm getting more of a numerical value to look at rather than contour lines. So I can see here, if we go ahead and turn on a few of these other sections across the slab, if I'm looking at my top reinforcement and I increase this section diagram, it makes sense that I'm going to need more reinforcement again around these column supports, because we have negative bending moment. If I take a look at my AS1 bottom, you can see I have significantly more reinforcement required at areas spanning between the supports. And with these sections, it's nice as well. I can always right-click and go to my results diagram, and I can view it maybe more so along the length in quite a bit of detail, more as numerical values. I can add in as many diagrams as I want. Let's say I want to view this section for all, for both top and bottom, and in both directions, 0 degrees and 90 degrees along the length. And now I can really compare what's going on in all my reinforcement directions. You can print this off as well, and quite a few quick links here. I can switch my sections at the click of a button. I don't have to necessarily go back to RFEM. I can also export directly to Excel. So that's certainly a useful feature if we're wanting to view things more as numerical values rather than contours. Okay, so now that we've done a basic strength design, we want to move on to a service design. So I can easily jump back into my add-on module by going to this drop-down box here and choose current module. And I'm now back in my concrete surfaces. So for this option, I'm going to choose copy case. And what the program's going to do is it's going to copy my strength load case, and I'm going to rename it strength and service with some basic reinforcement. So now I'm going to design for both strength and service, and I'm also going to take into account some basic reinforcement design. I click OK. So now you can see that I can jump back and forth to both cases. And by all means, you can do all of this within one case if you like. I'm just trying to show you guys a clear, distinct difference between all the different areas that we're applying these different design applications. So now we're under strength and service. I go under my serviceability limit state, and here is where I'm going to want to select all of my ASC load combinations. So you'll also notice I have an options down here. I have both analytical and nonlinear. Now this relates back to my PowerPoint when I was discussing the differences between RF concrete nonlinear, and that would be this option here, which we're not going to get into today. Rather, we're just going to stick with the analytical. This will be a linear elastic analysis. I go into my details here. And the first thing to note is that I have a couple design options. For my serviceability, I'm going to design for cracks. So I want to leave this checked. Now deflection, I'm going to leave this checked off. We'll get into this later in a little bit more detail, but for now I just want to design serviceability for cracks. The other thing I'm going to check off down here is I don't want to increase my longitudinal reinforcement for serviceability limit state design. It's just something for this example I don't want to do, but you can keep this checked on if you'd like. If you're not meeting your serviceability crack widths, for example, well, we can actually increase the longitudinal reinforcement automatically to solve that issue. So now that I've defined a serviceability limit state, my materials, everything's the same here, but notice my surfaces tab has a few more options. The tab down here, limit of crack widths. So the first thing that we want to do with our serviceability is to tell the program, well, what are my limiting crack values? You know, what can I base this ratio off of, and what's limiting the total width of the cracks based on the applied load? So the ACI committee did quite a bit of research and determined that there are, depending on where your structure is located, there are maybe some crack widths that we can follow for limiting dimensions here. So for our example, maybe we consider our structure in a very humid environment. Well, then I'm going to set my crack width under this selection as 0.012 inches. Now you want to control both the top and the bottom. You can certainly set these as different as well, but for our case it will be 0.012. We can also choose user defined. You know, maybe you have a different limiting value that you'd like to put in here. You can do that as well. Design without direct crack width calculation according to 2432. The ACI code tells us in section 2432 that it's not so much, you know, a given equation for what we should limit our crack width to, but the code tells us that we should really limit our spacing of our longitudinal reinforcement to decrease the cracking of our concrete. So by having this selected, the program will know to follow the stipulations that the code calls for in this section to limit our spacing of our longitudinal reinforcement. This other option, design with direct crack width calculation, this comes from more of a theoretical equation. It's the Gergely and Lutz equation. This essentially will calculate a crack width for us based on our applied loads and our specific elements that we've modeled. So by having both of these checked here, we'll see in our results what exactly is shown in terms of our ratios. Okay, under reinforcement here, everything stays the same except for when we jump to this longitudinal reinforcement. So initially I had left this blank, but now I want to provide some basic reinforcement. So what's nice is that we have this library that we can pull open here. Now, if you jump down to the United States, we have welded wire fabric reinforcement already selected here, or already an option to select here within the program. I know when I did design for precast concrete bridges, we only used welded wire reinforcement. So this is nice that you don't have to manually apply these specific properties of our reinforcement, but you can bring them up from this library directly here. For our example today, we'll probably be using reinforcement bars at a specific spacing. So that will be this option right next to it. You can see here that the only thing I need to do is to specify my diameter of my rebar. So maybe if we try number 6s, we'll use 0.75 inches for our diameter. And the rebar spacing, let's try 10 inches on spacing, or on center. And I'm going to apply this to both the top and the bottom, and both the 0 degrees and 90 degrees. If I click OK, you'll see the program automatically fills in the reinforcement area for all directions in both the top and the bottom. Additional reinforcement for serviceability state design. If I have a little drop down here, and if I click on this info button, this kind of gives me a little bit more information of exactly how this is being applied. Right now I'm just applying the provided basic reinforcement across the entire span of my slab, and then any required reinforcement will additionally have to be taken into account. With that, everything else stays the same, and we can easily run our calculation. Now, something to take note of, it will take a split second longer because now we're running all of those ASD load combinations as well for our crack width design. And we're still running LRFD to get our required reinforcement design as well. And it will bring all of these options, or all of the results, back into this add-on module directly. So as we saw last time, we have our required reinforcement. Nothing should have changed here because we didn't change anything in our external model in RFEM, but now we have a serviceability design available here. You can see that I now have my crack width control, my crack width ratio. I have my green smiley face because I am well below my design limit value that we set at 0.012. My existing value is 0.006. And you can see the information where this comes from, the Gurgley-Lutz equation that I explained before. We're actually calculating a specific crack width. We're also meeting the allowable spacings according to the code that we set in the limiting factors as well. Again, you can press this info button to get all of the possible information that you need and which location you're looking at exactly for how those calculations were derived. We can view each one by surface again, just like how we saw in our required reinforcement. Now we can view the cracks at each particular surface, and we can also view them by point. Again, we can jump to our graphics view here, and I'm going to turn back on my ISO bands, turn back off my sections, and now we have this whole serviceability limit state design. So I can actually view my contours for my crack widths as ratios. So you can see here nothing is in red, so nothing is greater than 1. I can view each crack ratio by the top, and this kind of makes sense what we're seeing. We would expect cracking to occur on the top near the columns where we have negative bending. As for the bottom, again, this is exactly what we'd expect. We expect to have cracking in between our supports on the bottom. We can also view the crack width numerically according to the Gurgley-Lutz equation for both the top in either direction and the bottom in either direction. And just like before, we can always turn on these sections here, turn off our ISO bands, and view them more numerically if we'd like. So that's also an option. So turning back on the ISO bands, and now that we've seen the serviceability design, we did add in some basic reinforcement. So we now have some additional options up here. I have my original required reinforcement for, let's say, my top and my bottom. This is nothing different than what we saw for before. But now you'll notice under my provided basic reinforcement and my little panel here, it's telling me I now have 0.53 inches squared per foot across this entire slab. No matter which direction I change it in, it's still 0.53. That's because we applied the same number 6s at 10 inches on center, top and bottom in all directions. Now, here's where the fun part comes in. So we provided these number 6s at 10s, but how does that compare to our required reinforcement? Well, we have a nice feature here called AS required over AS provided. This is showing us our ratios. You know, so if anything is over 1.0 here, then we obviously know that we have some issues to deal with in terms of adding more reinforcement. If we jump to our top reinforcement, we obviously have some areas near these columns and wall supports that we just simply need to add more reinforcement. The number 6s at 10 are not meeting what my requirements are. I can see that based on these contour lines. Same thing with AS top in the other direction, and then I can view my bottom as well. The bottom's a little bit better, but again, you know, maybe we have some overstressed situations down here where we have a longer span. So how exactly do we deal with that? Well, this is where we want to jump back into our RF Concrete Surfaces add-on module. And under reinforcement here, and longitudinal reinforcement, this is where we're going to now provide some additional bars at a specific spacing, maybe around those columns and wall supports. So under the Details tab and the Reinforcement tab, we have either the automatic arrangement of our reinforcement or the manual definition of the reinforcement areas. I'm going to choose manual definition. And you'll notice that the display really changed quite a bit when we selected that. We now have this provided additional reinforcement. So this is great for you as an engineer if you want to have a lot more control over where you're placing your specific reinforcement. If you want to tell the program, hey, this is what I'm going to put in, can you tell me if it meets what is required? And you'll notice that I have my provided basic reinforcement still here. We can certainly leave this in here and it will be applied to the entire slab just like what we had done before. But I'm actually going to zero these out because I'm going to apply these number 6s at 10 inches on center manually. And we again have several options here. We can apply it as a rectangular reinforcement, polygonal, circular. So again, you know, we really try and step out of that simple box that if you have this structure that requires some circular reinforcement area, it's no problem in the program. So I've zeroed out this provided basic reinforcement and I'm going to add that in by hand now. So I'm going to apply my rectangular reinforcement and this dialog box should look pretty familiar. This is similar to what we saw for our freeloads. And what we can do is simply select the surfaces. Again, if you have multiple levels of elevated slabs and you know you're going to reinforce these columns the same at every single level, well, this would be a great time to use the projection throughout all the different surfaces. Again, not really applicable in our case because we only have one surface here. The projection plane will be in the XY direction. Again, we can pull out this welded wire reinforcement if we'd like according to these rolls or sheets, or we can define our diameter of our rebar at 0.75 at 10 inches on center. Now, I want to apply this to both the top and bottom in the 0-degree direction. And I simply just choose my 2 points to apply my number 6s at 10, and I'm going to choose the entire slab here. I click OK, and now I have this table available that I can see I've applied to both top and bottom in the 0-degree direction, number 6s at 10 inches on center. I want to also use that same dialog box, but I'm going to change that to 90 degrees. The program remembers my input from last time. I click OK, and now I have top and bottom in the 90 degree. So the other thing to take a look at is we can view all of this visually. So now if I turn on my panel here, I can see I have 0.53 according to this table in all my different directions. Now the whole purpose of this was to add some more reinforcement around our columns. So I'm going to go back into this dialog box, and I'm going to change this back to 0 degrees. And let's say around our columns, we maybe will want number 8 at 8 inches on center. So quite a bit more reinforcement there. So our diameter will be 1.0. Our bar spacing will be at 8 inches on center. Now, instead of selecting 2 specific points, we can use this other option to select a rectangle. Now I can select the center of my column and simply expand this out so that my additional reinforcement is now as a rectangle around that particular column. I click OK. I look at my table. It's existing here in the 0 degree direction. I want to do the same thing again, and just all I have to do is change this to 90 degrees. And you can also use some copy and paste options in the table. I think it's easiest just to go into the dialog box again. That's the most user-friendly way to do it. And now if we view this, we can see that we have our additional reinforcement around this column. We can see the total number in inches squared per foot for both the top and the bottom. I can view all these different top and bottom views back in RFEM while I'm still looking at this table. Something to take note of, this is additive. So I added number 6s at 10 inches on center across the entire slab. Then I went in and added on top of that number 8s at 8 inches on center. So if you don't want it to be additive, you need to adjust your total reinforcement area to take that into account. The program does not override one area with another. As you can see here, the 1.71 includes both the number 6s and number 8s. Something else, this is not a perfect rectangle. The reason why is because we actually apply that additional reinforcement to the FE mesh elements. So you can see here that we kind of have a distortion here of these FE mesh elements, so that's why it's not a perfect rectangle. Overall, it's not a big deal, it's just how the analysis is done. Now, the next thing to do is we want to apply it to maybe these other columns here. Well, I could go back into my dialog box and apply it to this column, then this column, but we also have a very useful feature. If I just highlight my last 4 rows that pertain to this particular column, we have a move or copy feature. And what I can do is I can select one copy, and all I need to do is to click from one column to the other to define my displacement vector. I click OK, and now all of those options from this first column were also copied to the second column. So a very quick, efficient way to do this when you have a lot of repeat areas, such as columns like these, where you will simply need to have the same reinforcement at all locations. Now I can do the same thing for my last column with my move and copy. By just selecting my displacement vector, I click OK, and easy enough. Again, you'll see that it really is applied to the FE mesh, not as a perfect rectangle. So I probably want to do the same thing at my line supports here for my walls. You know, we had some high bending moments at these locations, so I want to do the same thing, but rather than take the time during this webinar to copy and paste and to draw those all in, I just will pull open another add-on or another model where I've already done so. So you can see here that I did the additional reinforcement to all of the wall locations. You'll also probably notice I left this column blank, and I just left it at the number 6s at 10 inches on center, and there's a specific reason for this. I want to show you guys back in RF concrete surfaces. So now that we've applied this to our different locations under my longitudinal reinforcement, you can see that my table is much more extensive here, much longer than what we saw before. And now what I want to do, and what's also great, is that now that I've defined these, I can go and run my calculation, and I can take a look at you know, my same reinforcement results, total. For the total required reinforcement, I still have my crack width telling me here what my serviceability design is, but you'll notice that I have something here. I have a message, 225. 225 down here, or I can click here, is telling me my longitudinal reinforcement one direction is not sufficient. No check possible. Well, the reason for this, if I go back into my graphics and we take a look at our required reinforcement, again, this is nothing different than what we've already seen in our other add-on modules. We can smooth the color transition here to make it look familiar to what we saw before. But now for my provided reinforcement, I'll click on my provided additional reinforcement here. Now this looks familiar for what we saw before. How about though we take a look at the not covered reinforcement? I'm at my AS1 in the top direction, spanning from left to right here, and everything looks to be 0, but that column location where I specifically didn't increase my reinforcement. So the program is smart enough to tell you that, hey, you simply don't have enough of your provided reinforcement to meet what we found for the required reinforcement. And that is specific to this column location. If I look at the AS top in the other direction, same type of scenario. You'll notice these other columns are okay. That's because we provided quite a bit reinforcement there. If we look at our bottom, you'll notice that everything is zeroed out. It looks to be just fine with the provided reinforcement in both directions for my AS required over AS provided. I can even look at those ratios again, and you can see quite clearly here where we've added more reinforcement and where we haven't. So you can see all of the red still occurring at this particular column. Well, so how do we deal with that? That's no problem. That's exactly what I was showing you guys before under longitudinal reinforcement. Maybe I want to take my rows here, 5 through 8. I'm going to use my move and copy tool, select my displacement vector. I click OK, and I can view this graphically now, and now we have additionally applied all of this reinforcement to this column. You'll notice that I don't have to solve for my strength load conditions again. That's nice because really that provided reinforcement can automatically be calculated by the program without an additional calculation to be ran. We do need to run the strength load combinations just to see how that reinforcement did affect it. So we can quickly run our ASD load combinations to get our serviceability limit state design for all of our surfaces. So now when we jump into our serviceability design, we can view our cracks. Everything looks good just as we expected. And now we have an actual reinforcement layout, maybe according to how our slab would actually be reinforced. And we just want to make sure that it's meeting these required reinforcement based on our applied loads. Okay, so that essentially sums up strength and service design. Now, the last thing that we want to do is to consider our deflection. And jumping back to, we're still in our concrete surfaces add-on module, but I'm going to create another load case. I'm going to copy this case, and I'm going to call it deflect. Now you'll notice that I still have my serviceability and strength limit states remembered here. And under my analytical, how we initially disregarded our RF concrete deflect, I'm going to check this now. And I'm going to consider long-term deflection according to creep and shrinkage for the duration of 60 months. So jumping back to the PowerPoint, what exactly does this mean? Well, the ACI code in section 242411 tells us that we do need to take into account consideration of shrink and creepage. This is due to things like temperature, humidity, curing conditions, a lot of external forces and such that really are out of our control but still affect our concrete design. So we want to take them into account for long-term deflections. So how do we do so? So you saw in RFEM, in RF concrete surfaces, that we have an option to consider the load duration. Right now the default is set at 60 months. So this will use a time-dependent factor of 2.0. This time-dependent factor is multiplied by our immediate deflection. Immediate deflection is easy enough to pull from RFEM, but in order to consider creepage and shrink, we want to consider this time-dependent factor. You can certainly put in any type of load duration in months as you'd like, and the program will calculate the appropriate time dependent factor. And then we will use equation 242411 from the code to apply this time dependent factor. In the commentary of section 24241, the code tells us that this equation can be used for both one-way and two-way slabs. So there is no differentiation here between one-way and two-way slabs. We should be able to do it for both. So tension stiffening is basically a consideration of the stiffening effect on our concrete in tension. So here, additional tensile strains beyond zero strain in the concrete will be considered when we do have this checked. So the default is to have this checked on. I click OK. Now when I jump down to my Surfaces tab, we have another option here in addition to our crack widths. It's called Deformation Analysis. So this is great because in the code, it tells us that we have some max possible deflection ratios that we want to meet for our slab design. This comes from table 2422. Rather than defining the deflection ratios for all my slabs at one time, I'm going to uncheck this box and check them individually. The reason for this is why I created 4 different slabs, because we have 2 cantilevered slabs out here that are going to have different deflection limits than our interior slabs that are simply supported. So for my slab number 1, I'm going to choose a user-defined relative deflection ratio. Maybe we want something like 240, which comes from the ACI code, and then I just simply need to define a reference length here. So my first slab, I will just use my measure tool. It will come out as 18.5 feet. Now, slab number 2, same exact scenario, maybe L over 240 is my limiting deflection. Here I can measure the side of my slab, which comes out a little bit longer at 27.5 feet, which we can see here from our dimensions that were drawn in. Our cantilevers, a different scenario here. Our L deflection ratio is maybe something more like L over 125. And we want to measure from the edge of the support to the cantilevered end. Same thing for slab number 4, user-defined L over 125. I can easily type in 9 feet here, or I can measure it again. Now, what is the deflection relative to? So most of us are probably familiar more with relative or absolute. Absolute is going to be in reference to the undeformed system. So basically, what is our deflection ratios? Are they from what the original structure looked like before loading, or is it more so we're going to measure the deflection ratios and take a look at the deflected end nodes of the 2 surfaces? We have a nice little picture here that kind of explains a little bit more if you want to understand what exactly these settings do correlate to. Typically, we'll use the undeformed system, and I will just leave that as the default. Reinforcement design, remember we're keeping everything exactly how we had it selected before, so we don't need to make any changes to that. So the only thing I need to do is just to hit my calculation button here. It does take a split second longer to calculate, so I went ahead and already solved this just for the sake of time so that we can easily pull this up. So if I were to run my calculation, what would pop up then is exactly what you're seeing here. I moved down to my serviceability design, and now in addition to my crack width, which you saw that we were just fine on, we're at 0.2 now, I have my deflection ratio. I have a red sad face here because we unfortunately are over 1.0 for our deflection. So the question is, okay, well, where's our problem? You know, how can we really view this? Well, I can view it still in my tables by my particular surface. It looks like surface number 4 is the issue, and the program will sync with exactly where this problem, and it's the cantilevered slab over here at exactly, it looks like about this center point where we have kind of an issue. Maybe we want to jump to our graphics here, and again we can view maybe our deformations. We can view it in terms of our local deformations. We can see that, sure, this is certainly an issue whenever we're looking at our concrete design. I can even turn on my regions or my sections here to take a look numerically by turning off these ISO bands. We have a deflection of 1.262. I can view this again by going to my results diagrams to view everything graphically here as well, and add any more of these deflections that I'd like to do. So how do we solve this issue with deflection? Well, there's quite a few options here. You know, reinforcement may control some of it. Obviously, we want to take a look at our applied loads, but probably the easiest way is just to jump back into our RF Concrete Surfaces add-on module, go to our Surfaces tab, and our original depth or thickness of our slab was set at 12 inches. Maybe we just want to increase this to 14 inches. And you can do so directly in the add-on module. I don't need to do it in RFEM. What's nice about this is if we're just kind of playing around with the structure, seeing what works, what doesn't work, I don't have to keep going back and forth into RFEM. I can do everything within this add-on module. You'll notice I get this notes message down here. I can check my messages. It says the thickness in RFEM and RF concrete are not identical. This is just a little warning in the program telling you that if you were to go back into RFEM and to do any more type of analysis, you'll want to change that surface thickness to 14 inches as well in there, just so that if you're doing any other type of analysis outside of this add-on module, it will be taken into account. So now I just want to hit that calculation button again, and once again, for the sake of time, I've already solved this, so I'll open up my other model here, and I jump into my RF concrete surfaces. And let's say we were just running our analysis here. Again, you can see I'm using 14 inches for the thickness of my concrete slab. And now under my serviceability design, I have my green smiley face. He's telling me that, okay, your design limit value is 0.864. After I increase the thickness of my slab, I'm now at 0.637. So everything looks great in regards to my checks in terms of serviceability. And we also know that we're already meeting our strength demands for our required reinforcement. So essentially, our surface design is done. A couple other things to note here. We do get asked if the RF concrete surfaces takes into account the differences of one-way versus two-way slabs. Yes, it does to a certain extent. Now, there are some differences with two-way slabs in terms of shear and bending strength that we simply can't take into account in this module alone. That would be more of our add-on module RF Punching Pro. This right now is only for Eurocode. So we do plan to implement the ACI code hopefully in the near future for punching shear checks for elevated slab design. We know this is important for elevated slab design as well for the ACI. So we plan to do that sometime in the future. One quick final thing here that I want to show you guys, if we go back to, let me go back to my current module. And I want to take a look at my graphics, my results, and my required reinforcement. I'm looking at the top here. I want to quickly show you how to export this into some additional programs. If we just go to File, Export here, we have the option to export as a DXF file. We have some other options here for reinforcement design, Nemeshek, Stracon. And if we're using a DXF file, we have this additional tab here where we can select our surfaces that we'd like to export, and we can export those ISO lines and ISO bands. We just choose the projection plane, we click OK, it's going to save our DXF file here. And then I went ahead and just imported this directly into AutoCAD. So this is everything taken directly from RFEM straight into AutoCAD. I haven't done anything with it here in AutoCAD. And you can see that we have all of our contours shown. We do have a color scale down here. And then you can further use this for your detailed drawings of your reinforcement and such. So that's essentially what I wanted to show you guys with exporting. With that said, that basically sums up the webinar today for design of our concrete surface. I know I went over quite a bit of information today. There is more information on RFEM as well as our add-on modules on our website at dlubal.com. I'll also place this as a recording on our website as well, so you'll be able to find that under our webinars option. I also encourage you to go online to view a few of our social media sites. YouTube is a great one because, again, we also put all of our recorded webinars on there as well. Our Dlubal blog is a bunch of frequently asked questions that you may find applicable to your design situations. Our email here at our Philadelphia office is info-us@dlubal.com. The phone number is 267-702-2815. We will have more upcoming webinars. I try and do one about once a month, so keep an eye out for those either on our website at dlubal.com under support and learning and webinars. I'll also always send out an email reminder to sign up for that. If you did want PDH credit today, that's no problem at all. Please email me at info-us@dlubal.com requesting that PDH credit, and I will issue that certificate to you. With that said, that concludes our webinar today. So I want to thank everyone for attending, and I do hope to see you at our next webinar. Thank you.